Here's a slightly more difficult problem. So it's almost the same as the last problem. We've got this big massive wheel, mass of big M. It has a radius of big R. It has a rope wrapped around it that eventually goes down. I'm going to make it a bucket this time. I'm going to call that a massive M1. The difference here is that it's got this crank handle on it at a distance of little r from the center of the pulley. You may have seen one of these. I can't draw it very well, but basically there's a piece sticking out toward us right here, and it has some mass, okay? And I want to know the acceleration of the bucket at this moment. Now I'm phrasing it that way because the acceleration would change if this bolt, as this bolt moves around, the torque from that bolt is also going to change. So I'm talking about like right here when the bolt with the handle, basically the crank handle, is like on a horizontal line with the center, okay? That's about all we can do. It's going to change as it moves around, so it's the best we can do. The difference with this one is when we get to the moment of inertia of this system, I have to find a total moment of inertia. Basically, I'm going to get the total moment of inertia, I'm going to add up all the moments of inertia of everything involved. So the disk and the bolt. If I had more, I'd keep going. So like keep adding until you get to the nth thing, okay? For this particular problem, the total moment of inertia is going to be the I of the pulley itself, which we're going to treat as a disk, plus the handle right here, I don't even know what to call it, the handle, yeah, I guess. That's too, H is for handle, everybody. H is for handle. Okay, I might as well put those in now. A disk is 1/2 mass of the disk, radius of the disk squared, and the handle, I shouldn't, but we're going to pretend that that's a point mass. So the moment of inertia of a point is mr squared. So in this case, that's the mass of the point is m2, and that point is at a radius of little r. So like this, okay? All right, so other than that, we kind of do this the same way that we did the last problem. So I do net force equals the mass of the linear thing, which is m1, times linear. This has mass times gravity down, tension up. Those should be in a line, sorry. And you know what, for kicks, let's make down positive this time. There we go. So if down is positive for this, when this moves down, this is going to unwind clockwise, which means clockwise is actually going to be positive this time. Keep that in mind when we get to the torques, okay? So for the linear thing, that means the net force on the left-hand side is going to be m1g minus tension equals m1a, okay? Now let's do torque. Net torque, let's go over here, equals total moment of inertia times alpha. Okay, so let's see, torques. We've got tension pulling down, and we've got the weight of this pulling down right here. Ooh, okay. So I've got two torques this time. Here's the pivot. So this one's going to cause a positive torque. So that's going to be positive t at a distance r from the axis, minus this one's going to cause a negative torque. So that is the force is m2g at a distance of little r from the axis. That's it for torques. And then total inertia is all of this u, okay, all of this and then I've got my alpha. Boop. Okay. Yuck. Yuckity yuck 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 yuck. This is the kind of problem where if you had numbers, you'd probably want to put them in. just to get, like, for instance, it would have been nice to find the total moment of inertia and just get a number and then I'd have it. And then I could just put that number here. But I didn't write any numbers down for this one, so I'm going to keep going with no numbers, even though it's icky. Okay, so I got one equation, two equations. Here's my third equation. Let's see, the point of contact is right here between the linear and the rotational, so this is going to be a capital R. Okay, now I want the linear A, the A of the bucket. Oh gosh, how am I going to do this? Okay, so I can do, okay, let's solve this for alpha. Alpha equals A over R. So I can put that there. Okay, and let's solve this for T. Let's see, move the T over there, move this over here. I get M1G minus M1A equals T. So I can take this and put it here. And then I can rewrite all of this. Okay, so rewrite all this. I got M1G minus M1A. I'm just going to do algebra at this point. If you want to turn off the video now, we're done with the physics. It's algebra now. Let's see. Oh wait, I'm gonna keep myself color coded. Why not? All right, so that's that term minus M2G little r equals 1/2 big M big R squared plus M2 little r squared, and then alpha instead becomes A over big R. Yucky! Well, okay. Let's distribute this R through here, so I get M1G big R minus M1A big R minus M2G little r equals, let's distribute the A over R through, so I get 1/2, okay, let me think about this. It would be big M, one of the R's cancels but not the other one, and then an A, plus M2A little r squared. Yes, I do believe that is correct. Checkity check, check. Oh, I hope that's right. I'll get angry YouTube comments otherwise. Okay. Alright, like terms, what do we got? We got A, there's another A, there's another A. Let's just move this A over there, and then I'll have all my A's on one side. So on this side, I'm going to have M1G big R minus M2G little r equals, I'm going to pull all the A's out too, so I'm going to have over here 1/2 M big R plus M2 little r squared. This needs to join up over here and it's being added, so it'd be M1 big R, and then I factored out an A of all those terms, and then this just needs to be divided over there. So it looks really and truly terrible, but it's not that bad. Let's see, let's pull a G out of the numerator. So G M1R minus M2 little r, boop boop. And then all of this is the denominator. Can I do anything to it? Nope, I can't. There's nothing I can pull out. 1/2 M big R plus M2 little r squared plus M1 big R equals A. Ta-da! Okay. So, if I had numbers, I should get a positive number because I said down was positive, and if I'm releasing it at this moment, I think it's fairly obvious that, well, okay, it's not fairly obvious. If M1 is bigger than M2, for sure the bucket will win and this will unroll. If M2 is bigger than M1, it would have to be bigger, not just bigger absolutely, but it would have to be like M2 times little r needs to be bigger than M1 times big R, basically, to make the bolt win and make it like roll up the bucket, if that makes sense. So if you changed this to like, instead of the weight of the bolt, if you changed it to like U pushing down on the handle, then that would, like with a very strong force, then that would win, and that's how you wind a bucket up on a pulley. So this looks terrible. I know, it looks absolutely terrible, but I would probably give you numbers, and then you could go and actually get a number for this and a number for a bunch of stuff, and then it would get easier. But that's our difficult problem. This was the important bit right here. Write that down.